Welcome to chapter 5, the first video on chapter 5, where we are going to talk about curves in R2 and R3. And for this first section, we are going to have an introduction and many examples of curves in R2 and in R3. Right, so as an introduction, we know that curves in R2 and R3 occur naturally as graphical representation of physical and mathematical processes. It is useful to have an exact analytical description for a curve, such as a formula. And this is because if you have got a formula, so if suppose you've got a curve which is a graph of a function f from which is mapping r to r, then we can use the formula to describe the points on the curve and also possibly discover properties of the curve by investigating f. But however, most curves are not actually graphs of functions, and in this chapter we are going to introduce analytical descriptions of curves in R2 and R3, which includes many curves that are not graphs of functions. Right. So let's start off with some definition. So a three-dimensional vector function is a function r bar from I to R3, where I is an unbounded interval in R. So we are mapping so we've got a function that maps from an unbounded possibly unbounded interval in R, and it's mapping to R3. And then if it is a two-dimensional vector function, what it just means is the R is mapping from an interval to R2. So the difference is where it's mapping to. So for three-dimensional R3, for two-dimensional R2. So as a remark, we have to have this in mind, that all the definitions and results which we are going to discuss in this section and the next one hold for both two-dimensional and three-dimensional functions. So we'll give definitions and results for three-dimensional vector functions, but knowing that these are also applicable to two-dimensional vector functions. Right. So let's look at another definition, or more rather a remark. Let R be a three-dimensional vector function. Then for every t in the interval, r of t is a vector in R3, and what it means is r of t is equal to x of t, y of t, and z of t. So we may therefore associate with the vector function three valued functions x, y, and z, where these are functions from the interval to r, and we call these functions components of the vector function. If you remember, when we defined vectors, we had components. So here we also have components of the vector function. As you can see, it follows from what we already know. Now let's look at an example. So consider the vector function r of t. So the vector function is a two-dimensional function, three-dimensional vector function, such that the first component is t squared minus t, the second component is root t minus 1, and then the third component is 1 minus t, and our interval is from 1 to infinity. Right. Then the components of this vector functions are x of t will be, so the first component is t squared minus t, so x of t is equal to t squared minus t. Y of t is the square root of t minus 1, and then the z of t is equal to 1 minus t, right? And so if we are given a vector function, then its range will be a subset of R3, right? So if it's a three-dimensional function, then uh, its range is going to be a subset of R3. If it was a two-dimensional vector function, then its range would have been a subset of R2. And this can be thought of as a curve in R3. So the range can be thought of as a curve in R3, and we call C the curve parameterized by R, and R is a parameterization of C. Now let R of t be equal to t squared plus t minus 1, where t is a real number, and we are going to show that x is in the range C of R if and only if x is equal to y squared plus 3y plus 2, and we also sketch the curve C. Right, so for the solution, so we know that a point x is in C if and only if x is R of t for some t, and this is coming from the definition, right? So therefore x is in the range if and only if x, the first component, is t squared plus t, and then the second component is t minus 1. And then so if we look at this, we can see that we can easily express t in terms of y by just putting the minus 1 on the other side, and then we get that t is equal to y plus 1. And then if we substitute that into the first component there, so we replace t with y plus 1, then we get that x is equal to y plus 1 squared plus y plus 1. So t is equal to y plus 1. So if we substitute that, and then if we expand here, we get y squared plus 2y plus 1, and then plus y plus 1 will give us that. And we know that if we get x is equal to that, then that is just the parabola with the equation that, and then if we sketch the curve, it will look like that. Okay, let's look at another definition, sorry, another example. So consider the vector function r of t, which is 1 over t plus 1, and then the second component t squared minus 1, and where t is between which is the interval minus half to 2, and then we want to also show that a point x in C is in C if and only if y is equal to x squared minus 2 over x, where x is the interval where x is in the interval minus a third to 2, and then we also sketch the curve. So let x be a point in R2, then x is in C if and only if x is equal to r of t for some t in the desired interval. And then what it means is the first component is equal to 1 over t plus 1, and then the second component is equal to t squared minus 1. So if we express t in terms of x, we can see that it's easier to express t in terms of x as opposed to expressing t in terms of y. Then we can see that t is equal to 1 over x, minus 1, right? And then so if we substitute the t in there in this second equation, yes, then we find out that y is equal to 1 over x squared minus 2 over x. And then also we want to find the interval for x, so we take the two values minus a half and 2, and then plug them into the in there, or rather in there, and then we find out that x is between the interval for x is between a third and 2, right? So basically what we have is c is the curve with the equation that where x is between a third and 2. Now we want to sketch the curve. So I think here it's supposed to be 1 over x squared instead of x squared, right? Now we want to sketch the curve, so we need some vital information to be able to do that. So firstly we have, if x is a third, then y is equal to 3, and if x is equal to 2, we just put in x is equal to 2 there, and you find out that y is equal to minus 3 over 4. So that is the range of our curve, right? Or the range of r, right? So the next thing is we find out what is the x-intercept of c. So how do we do that? We just say suppose y is equal to 0, and then we find the x value to be half, so that's where that's the x-intercept, right? The next part is to find the turning points of c. So how do we do that? We find the gradient or the derivative of the function, and then we equate it to 0, and we find out that there's only one turning point between the points that between the interval that there's only one turning point in the interval that we are looking at, that's between minus third and 2. So the turning point is x is equal to 1, and then we also find where the gradient is positive and where the gradient is negative, right? So because x is equal to 1 is the turning point, it means one side is going to be positive, the other is going to be negative, right? And then we can check which intervals is which of the intervals is positive and negative, right? So we see that from minus the third to 1 is where the gradient is negative, and then where the gradient is positive is between 1 and 2. So our graph looks something like that, right? And so therefore it means that we have got a local minimum based on the shape that we have just noticed now. So so we have a local minimum at x is equal to 1, and then we can find the y value for that local minimum. And then we want to also find out where the curve is concave upward and the curve is concave downward, and so therefore we find the second derivative, and then we find out that we find where the second derivative is positive and negative. One of the signs here should change, right? And therefore if we do that, so you can do that, and then you find out that the curve is concave upward between a third and 3 over 2, and concave downward on the interval 3 over 2 to 2. So based on that information, we can then draw the graph. So we know that it's from minus a third to 2. That is the interval that and that the curve is defined on, and then it starts off negative with a negative gradient, and then a positive gradient, and it is also concave upward here, and then concave downward there, right? So therefore we get um, that graph. So we're going to look at another example, I think 2 more examples, and then we will then stop the recording and continue, right? So let's look at example 5.1.7 in the textbook, and it says let r of t be equal to that, and if you look at it closely, you see that we are familiar with this. This is just a straight line through A and B. So the range is just a straight line of through A and B, right? And let's look at another example. So this one we didn't sketch the graph, but the graph is pretty easy. It starts from A and, well, it doesn't start from A and B. It cuts across the whole R2 by passing through A and B, right? So let's look at another example, and this is example 5.1.8 in the textbook. This is our last example for this video. So consider the function r of t, which is c cos t, c sin t, where c is a constant, a real number which is positive, and t is from 0 to 2 pi. We'll later realize that that is just an angle, right? And then so let's think of the range of r. So what we want to show is that x is equal to, is in C if and only if it satisfies that equation, and we know that this equation is just an equation of a circle with center the origin and radius c, right? So let's take a point in C, on C. Then we know that if the point is on C, there exists a real number such that x is going to be c cos t and y is equal to c sin t. So the real number that we are talking about is the t, right? So we therefore have that x squared plus y squared is just equal to so if we then substitute those, and then we see that cos squared t plus sin squared t is just equal to 1. So therefore this is equal to that, right? So what we want to show now is, so we have shown the first part, that if x is on C, then it satisfies this equation. Now we want to show that if x satisfies this equation, then it's on C. So consider a point such that x squared plus y squared is equal to c squared. We want to show the converse. That means that we want to show that x, this point, is on C, right? So we have to consider 2 cases. One where y is greater or equal to 0, and then where y is less than 0, right? So we start off with y greater or equal to 0, and then where t is between 0 to pi. So let t be the magnitude of the angle between the positive x-axis with origin in the direction of x. So what we are talking about is this angle, right? And our x is there. So we want to show that x has to be on C, right? So by the definition of the magnitude of an angle, cos t is equal to, we know that is the dot product over the norm of x, which is just that. And if we rewrite it, we can see that x is just equal to c cos t, right? So if x is equal to c cos t, then we can also find y by making y the subject of the formula, and we find out that y is just c, the absolute value of sine t. But because t is between 0 and pi, therefore what it means is y is equal to c sine t. And because x is equal to c cos t, y is equal to c sine t, it means that x is equal to rt, where which means that x is on c. Remember the definition of um, of c. It has to be something of this nature for it to be on c. So therefore we have shown that that is what happens. So suppose y is less than 0, and let alpha be the magnitude between the negative x-axis and the ray with the origins with the origin in the direction of x. So basically what we are talking about is, instead of, we are talking about here, and then the angle will be somewhere here, right? To be on this part, right? So what does that mean? What it means is one. So it means that t will be equal to pi times the alpha, and t has to be between pi and 2 pi, right? Because we are now looking at the second, and so for the first one we are looking at the first and the second quadrant. Now we are looking at the third and fourth quadrant, right? So if we find the magnitude of the angle, we then say cos alpha is equal to that, and then we see it's equal to minus x over the norm of x, right? And then what does that mean? That means that x is going to be equal to cos t, like that. Now because y is less than 0, we see that how do we find our y? Then it means that y is equal to the negative, because we know that it's less than 0, the square root of that, and then we get that that is minus c times the absolute value of sine t. But because t is in the third and fourth quadrant, we know that sine t has to be negative. So therefore the absolute value of sine t is equal to minus sine t, so that y is equal to c sine t. So x is equal to c cos t, y is equal to c sine t, so therefore x has to be in c. So we have shown so basically what we have shown is that x is in c if and only if x squared plus y squared is equal to c squared. So what it means is c, the curve, is just the circle with center 0 and radius c. What it means is that, and then we can then easily sketch the graph of the curve, and it is just a circle with center, whose center is on the origin, and then whose radius is c. Thank you. We will continue in the next video.